Thank you all for being here. Of course, thank you to the organizers for putting together this great program and inviting me to speak. I'm really happy to be here. So my goal over the next hour is to introduce how constructions in equivariant homotopy theory can be used to generalize classical enumerative results over the complex numbers under the presence of a group action. This is an equivariant homotopy meeting, not an enumerative geometry meeting, so I won't assume you even necessarily know what enumerative geometry is. I'll start by just giving some examples of what classical problems in the subject look like, and talk a bit about why we might be interested in putting a group action kind of on some nice ambient space and using equivariant homotopy to try to extend classical results. Then I will talk about kind of the tools of the trade by which we would do this. This is what I'm calling the enriched enumerative invariance. And then I'll end with some results and examples. So most of what I'm going to talk about is joint with Kirsten Wickelgren at Duke, but I will also talk about some results that are joint with Charanya Ravi at Tata. So I think let's just start with what is enumerative geometry. So enumerative geometry asks for the number of solutions to questions imposing specific geometric conditions. So enumerative geometry seeks to count solutions to questions how many things is nebulous, but I'll give you examples. How many things satisfy geometric conditions? So here's an example, and this is kind of the poster child example of an enumerative geometry. Every smooth, complex cubic surface. So that's a surface defined by a degree 3 polynomial. Every smooth, complex cubic surface contains 27 lines. If everyone in this room gave me a different degree 3 equation cutting out a smooth, complex cubic surface, every single one of them would have 27 lines. Here's another example. Every smooth chordic curve, so meaning it's cut out by a degree 4 equation, it's a curve cut out by a degree 4 equation. Every smooth chordic curve has 28 bitangents. A bitangent just means some line that's tangent to the curve in exactly 2 points. If you all gave me different equations for smooth chordic curves, they would all have 28 bitangents. Here's another example. Given given 8 general points, in P2, there are exactly 12 rational curves of degree 3, which we call cubic curves. 12 rational cubics through the points. And in fact, fun fact, if you like these kind of problems, there's a recursive formula in D for the number of degree D rational curves through 3d minus 1 points. And this is due to Conceivage. I think this is what he got a field medal for, in fact. So here are some examples of enumerative problems. We like that we didn't get 0, we like that we didn't get infinity, and we like that they hold in a lot of generality. And there are a lot of reasons kind of why people are interested in questions like this. These are foundational, like the core of algebraic geometry type questions, but they also span other subjects. So there are a lot of people working in symplectic topology who also are interested in enumerative geometry. Likewise, people in combinatorics. And why I'm kind of interested in problems like this is that a lot of these results have proofs that are topological. Many of these, all question mark, I don't think so, but many of these have proofs that are topological. Instead of maybe the usual algebraic geometry thing of taking the degree of the top Chern class of some like cleverly constructed vector bundle, often these have what I think are a lot simpler to state topological explanations. Maybe I'll do this one. So, for example, it's the case, let me let S equal the set of 8 points. All degree 3 curves through S, the 8 points, interpolate the same family of curves, whether they're rational or not. So there's a family, and really it's a fiber bundle. Over P1, such that the fibers of pi are a degree 3 curves through the S points. And we want to count exactly the fibers that define rational curves. And it turns out that you can do this by just taking the Euler characteristic of the total space of this fiber bundle. So there's a little bit of magic. You can compute this in 2 ways. In one way, you get 12. And actually, you can show that this family is isomorphic to the blow-up of P2 at 9 points. So it has Euler characteristic 12. And on the other hand, you can use the Hurwitz formula and say, hey, this is a fiber bundle, so its Euler characteristic should be the Euler characteristic of the base times the Euler characteristic of a fiber. And it turns out that only the rational fibers contribute to the Euler characteristic. So this is also equal to the number of rational cubics through S. So this is just one example, and it turns out all of the examples that I've written on the board have purely topological proofs, and I think they're kind of slick. They're pretty cool. So this is sort of my interest, and I haven't got into equivariant homotopy theory yet, but really any question in classical enumerative geometry that has an interpretation in terms of topological invariance, whether that be an Euler characteristic or in these 2 cases, these results can be obtained via Euler number computations. One could ask now, if you had a finite group action on your ambient space, maybe a group action on your CP2 fixing 8 points, a group action on P2 under which the chordic degree 4 curve is invariant, you could ask now not for the number of solutions as an integer, but for the number of solutions in terms of orbits. So maybe instead of counting 12 rational cubic curves, you're interested in orbits of the 12 rational cubic curves under the presence of a group action. And instead of asking for an Euler characteristic computation, you might ask for something like an equivariant Euler characteristic computation. So goal can we use equivariant homotopy to generalize classical enumerative results under the presence of a group action, orbits of solutions. And I wouldn't be asking this question unless I could answer it, so we can. that would be a terrible way to promote myself and promote this talk. So the answer is yes. I'll give you some examples. I'll talk about tools that you might think about using in homotopy theory that sort of naturally lend themselves to enumerative problems. You can imagine that some would, but maybe not all would. And we're going to look for answers. So we're going to look for answers in the cohomology of a point in the cohomology of a ring spectrum. So we want to give ourselves some flexibility to pick different rings that might have different computational advantages. And we want a little bit of a litmus test here. So we want to kind of know before we go in that this is going to have some applications. Why else would we be doing this, right? So we might hope that when G is the Galois group of C over R, that these equivariant enumerative invariants would help you count things over the real numbers. If you'll notice that all of the examples I've given only hold over the complex numbers, and they do have real solutions, and they're all different. There's often not an elegant, quick kind of way to kind of go from the closed field case to the real numbers. But anyway, this is what we'll do. Are there any questions before I get to the new stuff?
Do you have other applications in mind besides if you were looking at a different Galois?
Yeah, a lot of these problems kind of have a natural automorphism group acting. So cubic surfaces, you can ask if the automorphism group is finite. Likewise for plane quartics, and you might just be interested in orbits of solutions under the action of the automorphism group. Yeah. Okay. So let's talk about what constructions in equivariant homotopy kind of lend themselves naturally to computations in enumerative geometry. And the starting point is really the degree. In particular, it's because degrees and local degrees can be used to compute Euler numbers and Euler characteristics. Well, they compute intersection numbers, really. So let me remind you how the degree works in case it's been a while since you've seen it or taught it. Given x and y, let's say that they're compact, connected, oriented manifolds of the same dimension, let's say that I have some map between them, I have an induced push forward on homology which takes the fundamental class of x and maps it to d times the fundamental class of y for some d, and I can take the degree of f to be this d. This is a good definition, except that if you're like me, you're probably not going to actually compute this push forward, except for like the 4 examples you would think to give yourself, and there are many more manifolds than that. So remember that one of the triumphs of degree theory is that you can compute the degree locally. Might need f to be differentiable, but let's take a regular value. The set of points in the preimage is a finite set. And around each point in the preimage, you can find a tubular neighborhood such that if you collapse the boundary of the tubular neighborhood around the point in the preimage, likewise around y, you can define a map that I'll call f sub x, which is a map between n spheres. And the local degree of f at x is the degree of this map. And now we celebrate because we got ourselves into one of the cases that we would think to give ourselves, and we say, hey, the degree can be computed as a sum of local degrees. And this is independent of regular value. I'm going to make a choice not to write over there so that people on this side can see. All right, let's do this equivariantly. Let's let G be a finite group. B, a finite dimensional G representation. So given a map of representation spheres, SV to SV, let's assume for a second that f is transverse to 0. You can take the equivariant degree of f to be the set of points in the preimage of 0 considered as an element of the Burnside ring. So if 0 is a regular value, then the set of points in the preimage is a finite set. In fact, it'll be a finite G set, and you can consider it in the Burnside ring. If not, pick another regular value. You'll just get a degree in stabilizer in the Burnside ring of the stabilizer. And remember also a result of Siegel that says for all subgroups H of G, the following diagram commutes. So for any endomorphism of representation spheres, you can take this degree to get an element of the Burnside ring. And you can get an integer by taking the cardinality of the H fixed points. And it's the same integer that you would get if you took your map F and mapped it to the degree, the topological degree of the map on H fixed points. So in particular, I say this to say that we should expect that any enumerative result obtained as an equivariant degree should recover a classical enumerative result in the integers just by taking the cardinality of the degree. So we should expect that any equivariant enumerative obtained via the equivariant degree should recover the non-equivariant classical count just by taking the cardinality. Okay, let's do new stuff. So I'm going to define an equivariant degree for maps between G manifolds that aren't spheres. This is due to myself and Kirsten Mickelgren. Let's let G be a compact Lie group. Let's let E be a genuine equivariant ring spectrum. And let's let F from X to Y be a proper the equivariant map of smooth G manifolds of the same dimension if we follow our nose, we'd like this degree to be a push forward in E-cohomology or E-homology, whichever you like, of a fundamental class, and we'd like to actually be able to compute it. And lucky for us, Atiyah did a lot of great work. So there's a well-known construction using Atiyah duality. There's a proper push forward from the cohomology of X to the cohomology of Y, but it's twisted. And it's twisted exactly by the Thom spectrum of the tangent of the relative tangent complex. So we have a push forward. It's not a push forward from degree 0 to degree 0. It's twisted, but let's assume that F is relatively E-oriented. So let's assume that we have an isomorphism like this. So that we have what I'll call an oriented push forward from cohomology of X in degree 0 to the cohomology of Y in degree 0. And we can define the degree of F to be this oriented push forward of 1. E is a ring, so there's a 1.
Those are all equivariant homotopy.
Yes, thanks. Exactly. So this is a really good definition in the sense that it's kind of so closely mirrors classical non-equivariant definitions that you can't break it. You can't break it to a duality. But as in the classical case, we haven't made our lives easy in terms of actually being able to compute this. So I'm going to define the local degree. Maybe I'll just say that when E is the sphere spectrum and F is a map between representation spheres, this degree does recover the degree I wrote above. And maybe before I go on to the local degree, it's a good time to ask if there are any questions. Okay, so we have a degree. Maybe you're better at computing cohomology than I am, but it would be really great if we could get ourselves into a local degree case so that we're just computing the equivariant degree of a map between representation spheres, and then we'd like some kind of local to global principle that tells me that I can compute this degree in terms of local degrees, and then we'd really feel good about being able to use this degree in enumerative geometry. So let's do the local degree. Let's let y, little y, be a regular value. Let's say g sub y is its stabilizer. We know we have lots of regular values by Sard's theorem. What we don't know is that we have a regular value that's a fixed point. So let's just not assume that we need one. So now, let's draw the same picture again. Here's x, here's f, here's y. So now, the stabilizer of y acts on, of course, y, and it also acts on the set of points in the preimage of y. Potentially non-trivially. So you've got a bunch of points in the preimage. You'd like to find tubular neighborhoods around them such that you can do a Tom collapse and define a map of representation spheres. But the problem is that the stabilizer of y acts on all of these points, and it might act non-trivially on them. So in particular, you might have like one point that's fixed by the stabilizer of y, but you also might have a situation where you have like these 3 points in a stabilizer of y orbit, and so you can't actually find stabilizer of y equivariant tubular neighborhoods around all of your points in the preimage of a regular value. The best you can do is define a map of representation spheres for a stabilizer of X representation. So that's the best you can do, but this map that you get for every one point in the preimage of the regular value will be relatively oriented. You can pull this orientation back. To get a map from the cohomology of little x to the cohomology of little y. It's just that this is only stabilizer of X equivariant. we can define the local degree of f at x to be the degree of this map. In the cohomology of y. This is the local degree of f at x and now we'd like the global degree to be a sum of local degrees. And we can do that. So let's let G be a compact Lie group. E is a genuine equivariant ring spectrum. And F from X to Y, proper G map, a smooth G manifold. And they need to have the same dimension. I did say that, okay. And we're going to let little y be a regular value. Then the local degree, well, the global degree of f can be written as a sum of local degrees. But I'm not going to add up every local degree for every point in the preimage of the regular value. What I'm going to do is I'm just going to add one local degree for every orbit, and then take the transfer over the whole orbit from the stabilizer of the point in the preimage to the stabilizer of the regular value, and I'll sum over the orbits. This is not quite right. The global degree lives in the cohomology of big Y. These local degrees live in the cohomology of little y, so I have to pull this back to a point. And this equality holds in stabilizer of Y equivariant cohomology of the point Y. Okay, so what have we done? We're interested in enumerative geometry. We want to believe that there are some constructions in equivariant homotopy that would lend themselves to enumerative results. And I've defined the degree and the local degree. You'll kind of just have to believe me that it's computable because we've gotten ourselves into the sphere case via this local degree construction. And now what we're free to do is we're free to change our ring spectrum so long as the map is oriented relative to it. And you could ask for like enumerative counts given in, what have you, the representation ring, the Burnside ring, maybe MU, G. And this is where we're at. So I want to tell you some consequences of this and also mention an analogous result in equivariant motivic homotopy. Before I do that, any questions?
Yeah, I'm wondering if everything is absolutely E-oriented, say not relatively, but absolutely, does this somehow determine the global degree?
You have to be really careful because you might pick two different regular values that have different stabilizers. But if you could pick like two fixed points, then yeah, you'd be fine.
But in general, the global degree cannot be recovered from this formula.
I'm not sure what you mean.
I mean, this is a formula for the pullback of the global degree to little y from big Y, right?
That's right.
And I'm wondering if somehow under global orientability assumptions, the global degree would just be multiplication by an element that can be determined by this pullback.
Oh, I don't think that it would be like determined by the, I don't think it would be determined that way. But if you picked like, if you wanted to get something in the representation ring and you picked like 2 points that had the same stabilizer, and let's say the E was complex oriented, then you'd get the same representation. Thanks. Any other questions?
So the main reason you say that you want local to global principle to apply to enumerative geometry is because it's computable, or is there more?
Exactly. Yeah. It's computable, and you can even do better. Like, you could talk about it in terms of like a Jacobian. I'm just not doing that for the sake of time. But you can also, you can use it to compute Euler characteristics and Euler numbers. So can use to compute the equivariant Euler characteristic of a smooth compact G manifold. I'm going to say G is a finite group now. You can also use it, can use to compute the equivariant Euler number of a vector bundle with respect to a section some equivariant vector bundle of rank the same as the dimension x. Maybe I won't say, maybe I won't actually define this, but this is a construction due to Thomas Brazelton, a good friend of mine and a great mathematician. And anyway, we show that degrees and local degrees can be used to compute the Euler characteristic and the equivariant Euler number. Okay, so before I move on to section 3 of the talk, I just wanted to quickly mention a related joint work with Shranya Ravi at Tata. So every time I give this talk, some of you have seen this talk before, sorry. Every time I give this talk, someone asks, hey, you have this degree and local degree, which are a push forward in cohomology, and you have a local to global formula between them. Could you do this in equivariant motivic homotopy theory? So let me just say, without going into too much detail, yes, you can. So let's let K be a field. Let's let G be a finite group scheme. Over the field, we need the order of the group to be coprime to the characteristic of the field. Let's let X, Y, smooth G schemes, same dimension. Let's let F from X to Y be a finite flat LCI G equivariant map. Say that. Say relatively oriented. With respect to a motivic ring spectrum, E, and relatively oriented in motivic homotopy theory can mean a few things, but certainly the kind of strong definition that I wrote here also is one that you could think about. So there is a degree. Maybe I won't write down all the formalism, I'll just say there is a degree. There is a degree. In the cohomology of big Y. And you can compute it locally when you have a regular value that's closed, whose orbit is closed, and all points in the preimage have separable residue field extensions. So you have local degrees. When Y is closed, you know what, also I forgot something very important here. X and Y are smooth G schemes, and they're also G quasi-projective. You really need this in order to get a Tia duality, an equivariant motivic homotopy theory. So, okay, this little point Y is closed, its orbit's closed. And the residue field extensions are separable. So you have local degrees. It's a theorem due to myself and Shrani Ravi. I'm not going to write down all the assumptions, but it's this. That the degree can be computed as a sum over orbits of local degrees. And we need another transfer. This is an equality in the cohomology of a point, where I've done a little sleight of hand that I think maybe we'll hear more about later this week because there's a talk on equivariant motivic homotopy theory. But you want to think about that I as the inclusion. And you want to push forward along this map in cohomology to get the right kind of transfer to make this formula work. So that was it for my enriched enumerative invariant section. Now I'm going to actually count some stuff. Any questions? Maybe I'll just say this is like using the six-functor formalism of Huihua. See also six-functor formalism by Khan and Rabi for derived Arden stuffs. But we don't need that for this. That's just like promoting my friends. Okay. Examples of let's do some examples of enriched enumerative results. I talked a lot about the example of 12 rational cubics through 8 points before, because that's the one I'm going to do again. Maybe let me first define what a rational curve is. Again, I realize this is an algebraic topology meeting. A degree B rational curve, rational plane curve is a map from P1 to P2 given by evaluating some point on homogeneous degree D polynomials. Okay, there are infinitely many, but as we talked about in the beginning, we know that there are finitely many through 3D minus 1 general points. We have conservatives to think for this. So finitely many through 3D minus 1 general points. In P2, for example, there are 12 rational cubics through 8 points. Let's do this equivariantly. So let's say G is a finite group. Acting on P2, no restrictions, it doesn't have to be algebraic or anything like that. Let's let S be a G invariant set of 8 points, 8 general points. So I'm not saying pick 8 fixed points, I'm just saying pick 8 points such that the set of all 8 points is fixed under the group action. Can we count orbits of rational cubics? And again, I would not be asking you this question unless I could answer it. I wanted to make a joke that I'm not like at a career stage where I can ask questions I can't answer, but that's not very funny. It's actually like actively not funny, even though I'm laughing. Okay. All right. So question is above. There exists some element that I'm denoting like this. And this notation is motivated by Gromov-Witten theory, so if it seems random, I promise this is like not totally made up by me. There exists an element of the Burnside ring, or you could think about it in the representation ring that counts orbits, I'll just say counts, rational cubics through S equivariantly. Furthermore, I can tell you exactly what it is. It's equal to a sum over orbits of rational cubics orbits of rational cubics through S, and I want to take the Euler characteristic of a rational cubic, equivariant with respect to its own stabilizer group. I only want to count one for every orbit, and I want to take the transfer up to the whole group. And the way to interpret this, let's say we're in the representation ring, though similar statement for the Burnside ring. The way to interpret this is that all of these Euler characteristics of rational cubics, these are all equal to 1. And so instead of adding 1 to itself 12 times, take something that's rank 1, multiply it, take something that's rank 1, make it not rank 1, make it the rank of the index, and then add it over the orbits. So in particular, just say rank.
Normalized order heuristic is 1 or 2?
1. Yeah, it's a rational nodal cubic. So its Euler characteristic should be something like the Euler characteristic of a smooth cubic plus its Milnor number, which is 1. So anyway, you get some virtual rank 12 representation. Likewise, you could take the cardinality of the element of the Burnside ring. Yeah, I can talk a little bit more about why you get 1. Well, you don't get 1. Why you get something of virtual rank 1. If anyone is interested after the talk, but you can actually write down, like really concretely, an equivariant CW complex in many cases. Like in particular, when G is the Galois group of C over R, acting by pointwise complex conjugation, these rational cubics only come in like 3 flavors, and you can actually write down a CW complex for each possible flavor. So here's a corollary. When G is the Galois group of C over R, acting by pointwise complex conjugation, the cardinality of the fixed points of this element of the Burnside ring, so the cardinality of the fixed points is equal to the sign count of real rational cubics through S. This is called a Bell-Changer invariant. But it's a good sense check that if you make something equivariantly, you'd like to do some examples, and it's kind of hard to find points that are fixed in P2 under whatever group action you give me. But hey, here's a sense check. We can, from this equivariant count, get back a count of real rational cubics. Okay. I have 5 minutes left. There's one more result that I want to tell you. Okay, so what did we do? We just counted orbits of rational cubics through 8 points. There are other curves that aren't cubics, and there are collections of points that are not 8 points. Okay, so let's talk about how we can make this a little better. So let's count rational of degree D curves and Pn through M, P1 through PM points. Non-equivariantly, the way to accomplish this is using Gromov-Witten invariance by defining the moduli stack of stable maps. So let M0 n bar PNC, let's let this be the set of tuples, and here are kind of what's in that. We're going to take a stable rational curve, well, just take your rational curve, and take some points on it, m points on it. We want these PIs to be points of the P1. We want the push forward of CP1 to be D times the class of a line. Okay, so this moduli stack very quickly gets really complicated. If you start trying to change the PN, you start trying to change your homology class, but you should really just think about this as the set of rational curves with m marked points that have degree D in PN. And you have evaluation maps.
Sorry, is this like the interior? Like, I guess I'm confused by the bar. I think
Oh, maybe you want to take the bar away?
I don't know. I must, yeah.
Oh, I might have simplified a bit just to
No worries.
get through it, but we can talk about it. What's that? The bar is for compactification, but this moduli stack gets a bit like complicated at the boundary, so I was just kind of gonna blow through that, to be honest. So you have these like evaluation maps. For every I, and what they do is they take some tuple like this, and they evaluate the map on PI. Now, if you start with a point in PN, the fiber of the evaluation map over that point will be the set of rational curves that whose image passes through the point. We'd like to intersect like M conditions, and the way that we do that is we let, by abusive notation, P1 through PM, the Poincare duals of homology classes. We pull back all of the point classes, take the cup product, and we push it forward to a point. And this is how you define Gromov-Witten invariance for Pn, G is 0, degree D. So the theorem that I'm going to leave you with is let G be a finite group acting on Pn, let P1 through PM be a G invariant set points in Pn. There are E-valued Gromov-Witten invariants. homotopy of a point, for E, homotopy K-theory, so KGL, MGL, algebraic cobordism, and Chow. And I'm thinking about these as all as equivariant motivic ring spectra. So I was going to write down a little bit more, like I was going to tell you how these are defined. I think I'm out of time, and I'm over time, so I'll stop there. Oh wait, actually, let me just say one thing. There are already equivariant Gromov-Witten invariants in generalized complex-oriented cohomology theories due to Abizaid, McLean, and Smith. I don't want to totally discount that because it's really amazing work. These are just the first I know of that are defined algebraically.
Thank you. Following that in academic honesty,
Well, it's really amazing work.
are there any questions for Candace? Yes, Jen.
Is there a enriched version of Konsevich's recursive formula?
That would be nice. Not yet. I think the next step is really going to be to get some virtual counts. Well, actually, an equally valid next step would be to get a recursive formula, but either way, there's not one yet.
I was wondering, since you mentioned applications, and the Gallo group thing, if you thought about applications of this to doing counts for like the kind of things that physicists want to compute, and they do compute, but not really, like for like correlators for quantum gauge theories for like SUN or something.
Oh, I don't know. I haven't thought about that. It's a really interesting question. Yeah, and one that others have asked.
Other questions? Yes, Dustin?
So the example you had with conjugation on CP2, so depending on the G set, C2 set that you get, like what can you say arithmetically about these points? Or it seems like there's some kind of arithmetic information that
The sign count of real rational cubics depends on the choice of 8 points. So you could pick like 8 points that are all complex, you could pick 8 points that are all real, and you won't always get the same number. And so this G set that you get, it's virtual, so it has minus stuff in it, but in either case, it keeps track of how many of those points are real.
Thank you.
Yeah.
Anything else?
Maybe following up on that, is there a way to compute this G set like somehow independently of that? I mean, how do you apply this theorem in practice? Or like
To get the 12?
No, I mean, say you have your I'm just wondering how you somehow compute this, say this number n from just knowing the action without having to pick cubics, or is like picking cubics?
Oh, you would like a not local formula of it? Yeah, you can totally get one. So, non-equivariantly, I talked about that fiber bundle, X over P1, which was the blow up of P2 at 9 points. This holds equivariantly too. And so actually, if you just know that your P2 is like the projectivization of a rank 3 representation, anyway, you can use this isomorphism to write down another formula for that, which will give you like a rank 12 representation. Now you don't actually have to know what the Euler characteristics of each individual rational cubic are. Thanks.
Thanks, and that's how you do it in practice.
Yeah, exactly, and like if you have a holomorphic action, you can kind of split this up as like holomorphic tangent spaces. You can really do a lot in a representation ring. Yeah.
Okay, so let's thank Candace again.